Good evening. I hope you can see my screen. Okay. Someone's microphone is on. Can you switch it off? Okay, so in this tutorial, I'm going to cover a few GATE questions. So we have completed almost all the assignments from 1 to 12. So in this session, I'm going to cover a few GATE questions. Those are very important questions. So I'll not only cover what's asked in the question, maybe do the full question, right? Okay, Mr. J.K. Surya Narayana. Can you switch off your microphone? Okay, thank you. Okay, so before starting the session, I would like to ask you if you have any doubt for any previous sessions or any particular topic that you want to discuss. Okay, so I'll start with questions. So today I have 12 question total. So I'm going to do the solution. Okay, so these are previous year GATE questions. Okay, so a few simple questions. I'll start with simple questions. Okay, so this is one of the previous year GATE question. The transfer function of two compensators are given below, C1 and C2. Which one of the following statement is correct? Okay, so it's just a 1 or 2 marks question for the GATE, but you can actually do this question just by doing the Bode plot. Okay, without finding out all the coefficient KCT or alpha beta, right? So let me first do that way. Okay, so C1 and C2. Okay, for C1, so this is the transfer function. Okay, so you know how to draw the asymptotic Bode plot. Simply, you know, the corner frequencies are okay. So let me write in the form that we have studied. Okay, this is okay. So you know what is here, like for the C1 exactly. Okay, so what are the corner frequencies you can see? So 1 and 10, right? So 1 and 10. So you know 1 is, so let me write out here. One corner frequency is 1. Okay, and what we have a 0 here. Okay, and the other corner frequency is equal to 10, and we have a pole here. Okay, so this is rough Bode plot. Okay, so this is J. Okay, so this is in dB. Okay, so with respect to omega, I'm drawing it. So omega 1, you know, it's a 0. So what happens if you encounter 0? Okay, the slope increases. Okay, and at omega 2 we have a pole. Okay, so this is the Bode plot for C1. Okay, so you can just see this, and what can you tell me, just looking at this Bode plot, what this transfer function, like, is it the lead compensator or the lag compensator?
Sir, lead compensator.
Okay, clearly we can see it's a lead compensator, and other, you know, if C1 is lead compensator, Okay, we have to find out whether, okay, we have found out it's a C1 is lead compensator. Okay, other ways, you can find out looking at the transfer function. Okay, Kc alpha. Okay, we know this is lead compensator. Kc alpha is equal to 10 n 1 by t. Okay, is equal to 1. Okay, and what we know, alpha. Okay, let me write the generic transfer function here. Okay, so C1. That we have studied, right? And value of Kc is between, okay, Kc is greater than 1. And alpha is between 0 and 1. And t is greater than 1. Okay, this we know. And just we want to compare the two transfer functions here. Okay, so what is t? Here t is equal to 1, right? If we compare these two transfer functions, so t is equal to 1. Okay, and alpha t. Okay, so alpha t, looking at this denominator, is equal to 10. Okay, t is equal to 1. You can just substitute t. Alpha is equal to 1 by t. Okay, this also so because if you find out the three variables, because we know the like in variation of these three parameters, from here also you can find out the which compensator this is. Okay, let me do for C2, then it will be more clear. Okay, C2 is equal to, first we'll plot the Bode plot, s plus 10. Okay, and we have 10 into s plus 1. Okay, similarly, how I can write out this is s by 10 plus 1. Okay, so 10 is common, then again s plus 1. Okay, so this is equal to s by 10 plus 1 s plus 1. Okay, so let's first draw the Bode plot for C2. So this magnitude is in dB. Okay, with respect to omega. Okay, so corner frequencies omega 1 and omega 2. Okay, so what are the corner frequencies? Can you tell me? 10 and 1, right? So omega 1 is 1 radian per second. Okay, I'm not writing radian per second. So omega 1 is still 1 radian per second, and omega 2 is equal to 10 radian per second. Okay. Okay, but what we know at omega 1, what we have here, this is pole. Okay, and we have a 0 at, okay, so how it's going to be omega 1. Okay, we encounter 0, so slope will start decreasing. Okay, then we have omega 2. Okay, this is how again the curve will, then again you will have 0 dB per decade slope. Okay, so this is so this is opposite, right? So this we can say it's a lag compensator.
Sir,
Yes.
how to decide whether it is lag compensator or lead compensator, sir?
Okay, so we have studied lag lead compensator, right? So we know the properties of the lag lead compensator, right? Why we use the lead compensator, okay, to compensate for the phase margin, okay? But what are its disadvantage? What it does is, its disadvantage is this. So you can see here, it reduces the slope at low frequency, and you can see it allows, or it increases the gain at higher frequencies. Okay, that means we have a noise at higher frequencies. So this property of the lead compensator we know, right? That's why I have first drawn the Bode plot, right? Because we know the what what are the properties of lead and lag compensator, and then only we can decide based on that. Okay, so from the Bode plot you can see, okay, so it amplifies the higher frequency gain. That's why you can see from the Bode plot of lead compensator. So at higher frequencies, we have higher gain, right? And at lower frequencies, we have lower gain. That means it increases the steady state error. Okay, if you have studied the 12th week lectures. Okay, similarly for the lag compensator. Okay, so what it does the opposite thing, right? So what it does at higher frequencies, you can see it attenuates the gain, right? But that's what we want, right? We don't want noise in our system. That's what we want. That's why we employ the lag compensator. And again, one advantage of it is we are amplifying the low frequency gain. So what advantage it gives? It reduces the steady state error. Okay, these are the properties of lead and lag compensator. So we know that. Based on that, we draw the Bode plot. Okay, then we can see what this Bode plot is doing, and we can just by seeing the Bode plot, we can decide whether it's a lead or lag compensator, right? If you study the lag lead compensator, you also know like where the pole and zero and corner frequencies like. Okay. Again, if you if you don't know the Bode, if you're not able to find out through by drawing the Bode plot, you know about these parameters, right? You know the transfer function. So this is the transfer function, generic transfer function, right? You know the variations of each parameter. Kc should be greater than 1. Okay, alpha is between 0 and 1, and t is greater than 1, right? So based on that, you just equate your transfer function with the generic transfer function. So what we found out, okay? So here we have found out this. You see here, t is equal to 1, right? So it's greater than 0, not. Okay, Kc is also greater than 0. Okay, so this is what we have found out. Okay, so t is equal to 1, and if you substitute here, okay, alpha t is equal to 1 by t, and alpha is equal to 1 by t. So I know my range of the parameters, so I can just compare and see it's a lead compensator without knowing the Bode plot. Okay, for the lag compensator also similar thing we can do. Okay, so let me write the transfer function, generic transfer function that we have studied for lag compensator. Okay, so what was that? Okay, Kc beta this is beta is greater than 1. Okay, and in this case t was also greater than 0. I hope I'm writing it correctly. Okay, so let's compare with the given transfer function. Okay, you just compare these two values. Which value? Okay, you compare these two transfer functions. Okay, let's suppose we don't know the Bode plot. Okay, so can you compare and tell me what are the values for Kc, beta and t? Okay, let's first, what is the value of t? Just compare these two highlighted transfer functions. Okay, so you can see if you
So 1 by
just
10.
1 by 10, correct. Okay, similarly, if you compare the denominator, what you will get, you know, beta t is equal to 1, right? And t we know 1 by t, t is equal to 1 by t, right? So beta is equal to into 1 by t equal to 1, and this will get beta equal to 10, right? And from here Kc beta equal to, we know it's equal to 1, and beta is equal to 10, and k is equal to, okay, let me write different k here. Okay, so k is coming out to be 1 by 10, right? So you know beta, from one information we have is beta is greater than 1. Okay, so it all satisfied, right? T is greater than 0, beta is greater than 1, k is also greater than 0. Okay, from here also we can say it's a lag compensator. Okay, but it's better that you remember the properties of lag and lead compensator. Okay, because just by looking at the Bode plot, you can confirm which type of compensator it is. Okay. Okay. So any doubt in this question? So in this, if you see the options, which one of the following statement is correct? So C1 is lead compensator and C2 is lag compensator. Okay. So any doubt in this question? Okay, two ways you can do it. The best option, best way to learn is know what are the properties of lag and lead compensator. Okay, then you have to just plot the Bode plot and you can directly give the answer. Very simple. Otherwise, what you have to do, you have to remember the transfer function. Okay, it's easy. You know, it's a one pole, 1, 0. Okay, but still, the easiest option is uh, just to know the Bode plot of each compensator. Okay, we'll go to the next question. Okay, the phase margin of the transfer function GS is, okay, so we are given with this transfer function, you have to find the phase margin. Okay, so let's do all the steps to find out the phase margin. Okay. Okay, so this is the transfer function, right? So let's first find out the sinusoidal transfer function. So what we do, we place S with J omega, right? Okay, so you have to find out the phase margin, right? So what is phase margin? Phase margin is 180 degree plus the phase of sinusoidal transfer function at gain crossover frequency, right? So you should know the definition of phase margin. Okay, so we have to find out the phase at gain crossover frequency. Okay, so what is gain crossover frequency? Can you tell me? Because first you have to find out gain crossover frequency, omega GC. Okay, so before finding out omega GC, let me write out the like magnitude and the phase. Okay, so magnitude is equal to, okay, this is the magnitude, and okay, so it will be, this is the magnitude, right? Yeah. Okay, so you can cancel it, but I'm not canceling it. Okay, and the phase is equal to, so let me make space. So you,
Sir,
if
your
you see,
screen is
screen is what, visible or not?
not visible, sir.
Okay, can others also
Okay, sir.
confirm? Because I can see my screen visible.
Visible, sir.
Okay, you can just first log out and log in. I think some problem on your side. Okay, so let's find the phase. So, you know, in the numerator, what we have, 1 minus j omega. Okay, so this is for the numerator, and again for the denominator. Okay, so denominator, again what we have, minus 10 omega. I'm writing it like this. Okay, so what we can write, minus 3 into 10 inverse of omega. So any doubt in the phase why it is minus 3 into 10 inverse of omega? Okay, for the numerator it's minus tan inverse omega, because you know 1 minus j omega. Okay, so 1 minus j omega, it's in fourth quadrant, right? Fourth quadrant, how to find the phase? Minus of the angle, right? And for the denominator, the phase is tan inverse omega, but since it's lying in the denominator, okay, that's why we have minus sign. Okay, 2 times, because that's square, so I'll get this phase. Okay, so I have to find out gain crossover frequency. So what is special about gain crossover frequency? Okay, So this we have studied, right? At gain crossover frequency, the magnitude is equal to 1, right? So we have to find out at what frequency the magnitude is equal to 1. Okay, so 2. Okay, so this should be equal to 1, and now we have to find out this. So what I can write is this. Right, squaring on both the sides, what I will get 4, 1 plus, okay, so omega gc square is equal to 3, right? And because frequency is positive, so I'll take the positive, because if you take the root plus minus root 3, okay, I'll take the positive. So this is the gain crossover frequency. Okay, so at this particular frequency the magnitude is equal to 1. Okay, so first step is over. So again the next step is to find the phase at this frequency, right? Find the phase at omega gc. Okay, so let's find out. So we know this, right? 3 tan inverse of omega. Okay, from here. Okay, so let's find the phase at omega gc. Okay, because we know the value of omega here, omega gc. So what is that? 3 into tan inverse of omega gc is root 3. So what is tan inverse of root 3? Can you tell me what is tan inverse of root 3? Very, like, it's a very generic value. You should
60
remember.
degree.
60 degree, right? So it's coming out to be minus 180 degree. Okay, so what is phase margin? Phase margin is this 180 degree plus the phase at gain crossover frequency. So if I do this, I'll get 0 degree. Okay, so phase margin is in this particular question coming out to be 0. Okay, so here is the answer, 0 degree. Okay, but can we plot the Bode plot and see like how this looks like? Okay, let's plot the Bode plot for this. So GS is 2 into 1 minus S. Okay, so I don't know whether we can plot this. Okay, so it's a non-minimum phase system. Okay, we have the pole in the right hand plane.
Sir, 1 plus s whole square, sir.
This you're saying? Let me check. Correct. So it's a rough diagram. So what is the corner frequency? You can see it's only 1 radian per second, right? At 1 radian per second, what is happening? You have a 0 here, okay, and 2 poles.
Sir, your screen
Yes,
is not visible, sir.
screen is not visible. Okay, so others, can you confirm like screen is visible or not?
So it's visible.
Okay, you can, I think, log out and log in. Some problem on your side. Okay. Okay, so this is the corner frequency, right? So can you tell me what is the slope? Okay, let's find out the slope at higher frequency. So you know magnitude is equal to, this is the magnitude. Okay, I hope everything is correct. Yeah, let me write it. Okay, so this is the magnitude, right? And at low frequencies, you know, low frequencies, what is the magnitude? Okay, if you just neglect omega square as compared to 1, so in the numerator you'll get 2 and in the denominator you'll get 1. So it's like constant, some constant value, okay? And in dB it will be negative value, some negative value, but we are not concerned about that, okay? So at higher frequency what we have, you know, at higher frequency, so what is the magnitude we are getting? Okay, so this is, you'll get 2 omega by omega square, okay? So 2 by omega, something like that, okay? Because let me write it. If we neglect 1, okay, and we have this, so I'm writing, from here I'm trying to find out the slope at higher frequency, okay? Okay, I think, okay, Surya Narayana, can you please switch off your microphone? Yeah, thank you. Okay, so okay, let's find in dB. Okay, so what you'll get, 20 log 2 minus 20 log of omega, right? So what you'll get if you take 1 decade more than omega, okay? So let's take, this is omega, let's take 10 omega, okay? Find out the slope. So what you'll get is 20 log of 10 minus 20 log of omega, okay? So if you compare, okay, okay, so this is same, right? This is same. So only difference is 20 log 10 is, again, you know, it's equal to 20, right? So only the magnitude has decreased by 20, right? So what we can say, if we go 10 decade higher, that means magnitude is decreasing by 20. That means slope is minus 20 dB. Okay. So this is minus 20 dB per decade. Okay. But we are not concerned about this. What we want is this. So what is the gain crossover frequency? We got root 3. Okay. So okay. Okay. And also what we need is phase information, right? so we know this is how it looks. Okay, and here also we know magnitude. What is the magnitude? Okay, so at lower frequency the magnitude is 2 constant. Okay, so this is some 20 log of 2, which will be negative. So I'm writing in dB. Okay, but we want to plot the phase also. Okay, so what we have seen, so you know at this particular frequency, because this frequency, why it is omega gc. Okay, so let me consider this as 0 dB. Okay, I hope this is not correct. Okay, so 20 log of something is negative, right? So what is 20 log of 2? Can you find out? This is base of 10. We'll get some negative value. What is that?
Sir, 0.6.
This is minus 0.6, right?
Sir, 0.6 on the positive number.
Okay, this is 0.6, correct. So that's why, okay. So this is 0.6 dB. Okay, and when the magnitude becomes equal to 1, that means you have 0 dB, right? Okay, so at this particular point, okay, this is omega gc, right? So the magnitude becomes 1, or in 0 dB what you will get? Sorry, in dB you will get 0 dB, right? So at that particular point we have phase equal to minus 180. But if you look at the formula for phase, what I was getting, so phase was J equal to 3 into 10 inverse of omega, right? And I'm finding, I try to find out the phase at higher frequency. That means if I put omega equal to infinity, what I'm getting finally phase. So what is this value? If I put tan inverse of infinity is what? 90, right? So what is this? 270 degree, right? Okay, so we have found out the phase from here. Okay, so that I'm using it. Okay, so ultimately at higher frequencies the phase should be equal to minus 270. Okay, so let me, this is 9, so let me say this is 270. Okay, this is minus 90. Okay, what will get 0. Okay, because we'll start from 0 and will ultimately reach to minus 270. Okay, so
Sir,
yeah,
sir, low frequency magnitude, sir, it will be 6, not 0.6. Sir, 20 into 0.3010 is equal to 6.
one
Approximate.
second. So it will be equal to how much?
Sir, approximately 6.
Acha, 20 log 2 is what? 6.
Sir, 20 into 0.3010 is equal to 6. Sir, log 2 is
Okay.
equal to 0.30.
Okay, you said this. Okay.
0.3010.
So 0.6 into 20 is 6 into 2 is 12 dB.
No, sir. Log 2, sir. Sir, magnitude of log 2 is equal to 0.3010.
Okay, let's take 0.3. Okay, 0.3 into 20 is equal to 6 dB, you're saying.
6.
Okay.
Yes, sir. 60.
So it's a 6 dB. Okay. Okay, 6 dB, right? fine. Thank you. So 6 dB, we are starting with 6 dB and ultimately reaching. So this is how the plot will look like at higher frequency. So we are drawing the phase plot. Okay. So phase plot should go like this. Roughly I'm drawing it. Okay. Try to find at omega equal to 1 what is the phase. You'll get some negative value. Okay. And at omega will go to, okay, 270 degree. So this point, that why it was stable, unstable, because we are hitting this point. Okay. So phase margin, you can see what is the phase margin here, equal to 0 degree. Okay. And what you can see at gain margin, can you tell me? Okay, we have in this question we have found out the phase margin. Can you tell me what is the gain margin here? So we calculate the gain margin at phase crossover frequency. Okay. So phase crossover frequency is the frequency when the phase is equal to minus 180 degree. Okay. So at the same frequency, this is also the same frequency, right? Because at this same point we are getting the two. Okay. So any doubt in this question? This is just additional. We just have to find out the phase margin. That's it. Okay. I was just trying to realize like how to draw the Bode plot here. Okay. But you will not encounter this type of problem because it's a like it has a right pole in the right half plane. Okay. Usually you will not get. Okay. Let's go to the next question. Okay. So the frequency response plotted in the complex plane. So we have to find out the Nyquist plot, like corresponding to this GS, though GS is not clear. So let me write 1 by S into S plus 1 to S plus 2. Okay. So we have to find out the frequency response. Okay. Plotted in the complex G of omega plane. Okay. So it's basically asking to find the Nyquist plot. Okay. So what is the procedure? Okay. First is find the sinusoidal transfer function. Okay. So what we do, just replace S with j omega. Okay. And again, we try to find out the magnitude, phase, real and the imaginary part. So first find out, let's find out the real and imaginary part. So what I'll do, I'll just find out this transfer function in terms of real and imaginary part. Okay. So it will be minus j by, if I multiply for the first part. Okay. Okay. So this I have done. So what I have done, just multiply this with 1 minus j omega, 2 minus j omega in the numerator and the denominator. Okay. So in the denominator it's clear, in the numerator this is the value. Okay. So let's multiply in the numerator so that we get in real and imaginary. Okay. This is 2 minus j omega minus 2 j omega. Okay, again this will be plus, but j square is there, so minus omega square. Okay, again okay, so 2 minus omega square minus 3 j omega. Again the denominator. Okay, I'm not writing. So what you'll get? So 3 omega. Okay, and if you do this, you'll get this 2 minus omega square. Okay, but just you can write like this also, omega square minus 2. Okay, and the denominator is okay. So this is the, so we have now in real and imaginary part, okay, in the numerator. So again, let's see like if I made any mistake. Okay, let me write this as real part of j omega is equal to 3 omega by omega 1 plus omega square 4 plus omega square. Okay, so it is 3 by 1 plus omega square into 4 plus omega square. And the imaginary part is so what is the imaginary part? Omega square minus 2. Okay, this is the imaginary part. Okay, so what you want to do is first, okay, so from, because we want to plot from 0 to infinity, right? Okay, for the positive frequencies. Okay, so if you see for the positive frequencies, the real part is always positive, right? Omega square. So this is always positive, right? Real part is always positive, okay, for omega varying from 0 to infinity. But for the imaginary part, if you see, okay, so omega, so we have two regions, right? Omega less than root 2 and omega greater than root 2. Okay, can you tell me for omega less than root 2, so imaginary part is positive or negative?
Sir, negative.
Okay, so in this case it's negative and in this case it's positive, right? Okay, you just put some omega value and see here in this equation. Okay, so what we can see, real part is always positive, but imaginary part is, okay, real part is where, so I'm getting positive, okay, because from the graph, okay, I should not get positive, somewhere mistake I have done. Okay, so here, from here you just check the steps. Okay, so the second part is correct. Okay, so this part, okay, so I'm just writing, so we are multiplying j into minus 3 j omega, right? So what do you get? Positive 3 j square. Okay, first I write j square into 3 omega, right? Okay, so I'll get minus 3 omega. Okay, so one mistake I have done here. Okay, can you verify minus j into minus of 3j omega square. Okay, so minus minus becomes plus, then we have j square into 3 omega, so j square is equal to minus 1. Okay, so minus 3 omega. So that's why, so this is the value for every value of omega. The real part is always less than 0, and for the imaginary part we have two options, right? For omega less than root 2 it's negative, and omega greater than root 2 it's positive. Okay, so what we can expect, because I want to plot this g of s. Okay, so what is real part negative and imaginary part negative? This is third quadrant, right? And the real part negative and the imaginary part positive, this is second quadrant. Okay, so I'll get the Nyquist plot in these two quadrants, right? Because real part is, I know it's always negative, and the imaginary part is, it depends on omega is greater than or less than root 2. Okay, at least up to here everything is clear. Okay, so we know where the Nyquist plot is going to lie. Okay, so let's again find out, because g of j omega, the magnitude, directly we'll write omega into root of 1 plus omega square, and 2 square, which is 2 square plus 4 square. Okay, so yeah, and the phase is minus 90 degree minus tan inverse omega minus tan inverse of omega by 2. Okay, please ask if any of you have any doubt in this. Okay, how I am writing the phase and the magnitude of this transfer function. Okay, very simple, because all the terms are in denominator. That's why for j omega I'm writing minus 90, and for other terms we have minus tan inverse omega and minus tan inverse omega by 2. Okay, so let's build a table for different values of omega, real value of j omega, okay, and imaginary values. Okay, so we'll take two extremes, right? So let's find out at omega equal to 0. Okay, so at omega equal to 0, what is the real part? Can you plot, can you put omega equal to 0 in real part of g of j omega? What is the value you're getting? Can you see? Minus
Minus 3 by 4.
minus 3 by 4, right? Minus 3 in the numerator, and the denominator, if you put omega square equal to 0, what you will get? 1 into 4, that is 4, right? So minus 3 by 4. And let's check for the imaginary part. Okay, so imaginary part, what you can see, omega equal to 0 if you put. Okay, so anyway you are here, right? You know imaginary part is going to be negative, but what is that value? Minus negative, right? Just put omega equal to 0, what you will get? Minus 2 by 0 you will get, right? Okay, so in the numerator 0 minus 2, and in the denominator 0 into, what you will get? 4. Okay, so again, so let me write, this will be minus 2 by 0. Okay, which will tend to minus infinity, right? Okay, so what is the magnitude? Magnitude will be some infinity. Okay, so let's find the phase. At omega equal to 0, you can see what will be the phase. It will be minus 90, right? I think this is very clear. Phase we know, if you put omega equal to 0, so only remaining angle is minus 90. Okay, see here. Okay, so again, this is there. Okay, for gate quotient, it's very simple. You just, because, okay, minus 3 by 4 is there. So, you know, you have calculated, what you know up to now, real part is minus 3 by 4 and the angle is what? And the angle is minus 90 degree. Okay, and we are in the third quadrant. So directly what we can do, we can directly take this, right? This is the only option that is satisfying our conditions, right? You don't have to solve the entire problem, right? But we'll solve it. Let's see. Okay. So this we have found out. Let's find at omega equal to infinity. Okay. So what is the real part? So if you put omega equal to infinity, what you will get? 0, right? Okay. Just put omega equal to infinity. You will approximately get 0. Okay. And for the real part, okay. So what is real part? This is the real part. Okay. Put omega equal to infinity in this. What you will get? Again, you'll get 0. Because in the numerator you have omega square and in the denominator you have omega into omega square into omega square. So in the denominator we have omega raised to power 5, okay, which is greater than the numerator, and 1 by infinity, you know, is equal to 0. Here also you'll get 0. Interesting part is this. Okay, so phase is what? Minus 90. Okay, so minus tan inverse of infinity, again it will be 90, and minus tan inverse of infinity by 2. So this will be how much? 270 degree. Okay, so we have two conditions. Okay, so let's plot the Bode plot. Sorry, this is Nyquist plot. Okay, for 0 at omega equal to 0, what we had this condition. Okay, we know the Nyquist plot is going to lie in second and third quadrant, right? Because it depends on omega equal to 2. We will also find what will be the value of g of j omega at omega equal to root 2. Okay, so but we know where it starts, right? At minus 3 by 4 the angle is minus 90, so somewhere here, right? So this is the starting point, omega equal to 0. Okay, and this point is minus 3 by 4, and the ending point is where? Ending point is at 0 origin, real and imaginary part both are equal to 0, and again if you make the, what is the angle? Minus 270 degree, this one, right? Like this angle will be, okay, so this is the final point, right, at omega equal to infinity. Okay, so it's going to cross, because we know already, we have found out, right? For omega less than root 2 it's negative, and omega equal to omega greater than root 2 it is positive, right? So here, somewhere here, we'll have a point where, okay, we'll cross from negative to positive, right? Like this. Okay, so this is approximate. Okay, so this point is omega equal to root 2. Okay, so this is the crossing point, right? So let me just mark this. This is when, let me mark with red, omega less than root 2. Okay, and the other point is this. Can you find out what is the value, what is the magnitude here at omega equal to 2? Just put omega equal to root 2 in this. One by root 2 into 1 plus 2. Okay. So 2, this is 4, 4 plus 2. Okay. So what is this value? Root 2 into 3 into 6. Okay. Whatever that this value is, that will be here. Okay. This value. This value is, so I'm writing g of j root 2. Okay. So this is the complete Nyquist plot. Okay. So this is g of s plane. Okay. So you know answer is this point. Okay. So this point here is omega equal to root 2, because at this point we are crossing from third quadrant to second quadrant. Okay. So any doubt in this question? Okay. Typical what we used to do, write the sinusoidal transfer function, find out the real and imaginary part. Okay. So just by finding out the real and imaginary part, you ensure that you will know that this Nyquist plot will lie in second and third quadrant. Okay, because real part of g of j omega is always going to be negative, and the imaginary part is going to depend on value of omega. For omega less than root 2, you have negative value, and omega greater than root 2, you will have positive values. And you know the find out the magnitude and the phase. Okay, so at 2 points you find out. Okay, because you know it's going to cross, right? And we know the crossing point also. So it's very simple to draw this Nyquist plot. So from 0 to infinity. So any doubt in this question? I hope there is no doubt. Okay. Since it's a great question, you can just do one step and you can find out the answer. Okay. But we have done the full Nyquist plot. Okay. Let's do this. The asymptotic approximation of log magnitude was a frequency plot of system containing only real zeros and poles and zeros is shown. Its transfer function is. So we are given with a Bode plot and we have to find out the transfer function. Okay. It's also very simple. Let's first find out the frequencies, corner frequencies. Okay. So you can see what are the corner frequencies where the slope is changing, right? So you can clearly see one first corner frequency is 2, right? And what is, okay, let me just zoom. Okay. So at 2, the slope is changing from minus 40 dB to minus 60 dB. So can you tell me at this particular corner frequency we have a pole or zero? So at 2 we have a pole. Correct, right? Because slope is decreasing further. So so this is pole. Okay, so next corner frequency we have is 5. Okay, so at 5, so you can see slope is changing from minus 60 to minus 40. Okay, so what we have, so it's opposite of what we have seen for omega 1, right? So it's a 0, right? Minus 60 to minus 40 again. Okay, and the other corner frequency we have is 25. For this case, the slope is changing from minus 40 to minus 60. Okay, so that means again we have a pole here. Okay, total we have 3 corner frequencies. Okay, okay. So how can we write this transfer function? Let me write g of s. So we don't know the value of constant. but we know the corner frequencies, right? So we have a 0. So in numerator, we'll write like this. And in the denominator, we have 2 poles. Okay, this you know. Up to now, it's clear, right? Okay, so you need to find out the value of k. Okay, but one important information we are given with is this. Okay, at omega equal to okay, one more information here. Okay, so you have to also account for the initial slope. Okay, so this is the initial slope, right? So minus 40 dB per decade. So what can you tell about this? It tells about how many poles we have at origin, right? So what does this minus 40 dB per decade convey to us? So I already told you, we have some poles at origin. So how many poles we have at origin? Just by looking at the slope, you can tell me. Okay, so minus 40 dB per decade. Okay, that means we have 2 poles here. Okay, so this is the transfer function. Okay, but you have to find out the value of k. Okay, but for that, one information is given to us. At omega equal to 0.1, the magnitude is equal to 80 dB. Okay, let's use this information, okay, to find out the value of k. So let's find out. Okay, first the sinusoidal transfer function. Okay, so this is the magnitude, right? So let's first find out the magnitude at omega equal to 1. Okay, but we can do some approximation, right? You can see. Okay, so in this case, omega is very we are actually doing a low frequency approximation. Okay, omega is very small, omega equal to 0.21. So if you see the terms, okay, these terms, what you'll get, just compare 1 with 0.1 square by 25. Okay, if you just see the numerator, okay, you'll know, you calculate the value also, you can approximate this to 1, right? Because you know this very less than 1. Okay, similarly you can do for other 2 terms, right? So you'll have, so let me not put this 1 into 1. Okay, so this approximation you have done. Again, in the denominator also you can do this. Okay, as compared to 1, the value is very small. That's why we are neglecting it. Okay, but you're getting this, right? K by 0.1, that is what we can write. 100k. Okay, so how I have written 100k? So in the denominator it was 0.01. Okay, so what can I write here? 100k, right? So in dB it's given as 80k. Okay, so let's convert this into dB. This is 20 log of 100k. Okay, so we are given this 80 dB, right? So let's find out the value of k here. So what you're getting? This is 4, right? So if you take, this is 10 is to power 4. Okay, so what you're getting? K as 100, right? Okay, so you're getting k to be 100. Okay, so let's finally write the transfer function. K was equal to 100. Okay, s by what was the s by 5 plus 1, s by 2 plus 1, and s by 25 plus 1. Okay, n square was there. Okay, so what are the options? Okay, options are given in other form. Okay, so okay, so we'll get 1 by 5. Okay, so this is s plus 5. Okay, so we'll get s square, s plus 2, and s plus 25. Okay, which is 1 by 2 into 1 by 25 you'll get. Okay, let's solve here. So what you'll get, 2 into 25, this is 5. Okay, again the rest is here. Okay, so what are you getting? 1000, right? You're getting here 1000 s plus 5, s square, s plus 2, s plus 25. So this is final transfer function you're getting. Okay, so you could have written like in this form, pole zero form early, and you could have solved it. Okay, but since we have studied the Bode plot in this form, that's why I've written. So the correct option is this one. So any doubt in this question? So you need to be careful for this P and D option, right? Only constant is difference, otherwise everything is same. Okay, so any doubt in this question? Okay, so it was very easy to find out the poles and zeros. Okay, but what was required to find out the k? Because P and D options are same, only difference is k. For k, if you see the Bode plot, one more what information we have used at 0.1 omega equal to 0.1, the value is 80 dB. So that's why you have to find out the magnitude at omega equal to 0.1 and equate that to 80 dB, and you'll get the value of k. Okay, any doubt in this question? Okay, go to the next question now. Okay. So this is also related to Bode plot. Okay, so assume today Bode magnitude plot of a minimum phase transfer function. Okay, it's a minimum phase transfer function shown in the figure. This transfer function has. Okay, so it's very easy. This question is very easy. You can just within seconds you can do. Okay, let's also find the transfer function for this. Okay, So first solve this question. Okay, so you know the corner frequency first is, you know, it's equal to 0.1. Okay, and what is happening at 0.1? The slope is changing from minus 40 dB to minus 20 dB per decade. Okay, so what we can say, the slope is decreasing, right? So you can say it's a, there is a zero, right? Okay, then the slope stays constant until this point. Okay, so we have another corner frequency that we don't know, but what is happening at this omega 2? So I have referred that as omega 1. So at omega 2, the slope is changing from minus 20 to 0 dB. Okay, so what we have here, again, one more 0, right? Okay. We can actually find out, right? So because values are given at omega 1 and omega 2. Okay, so at omega 1, the magnitude is 20. Okay, and at omega 2, the magnitude is minus 20. Okay, so we know in one decade, the slope, the magnitude is decreasing by minus 20 dB. Okay, so what I mean by this, if you go from 0.1 to, let's say, this frequency 1 radian, okay, so that is 10 times, right? So let me just clearly, so we have omega equal to 0.1, omega equal to 1, and omega equal to 10, right? So clearly you can see 1, 2, and 3. Okay, so omega 2 is 10 times of omega 1 and omega 3 is 10 times, right? 1 decade. So this is 1 decade, right? That's what I'm saying. And from the Bode plot, I know the slope is decreasing by 20 dB. So what I'm referring to this slope, okay, by 20 dB per decade. Okay, that means at 0.1 it is 20 dB, then at some frequencies, that is 10 decade, 1 decade, that means at omega equal to 1 it should have 0 dB, right? So this is 1, and again if we go 1 decade above, that is 10, okay, then the slope will decrease to minus 20. Okay, that is what is happening. So am I clear, like what I have said? Are you clear? Okay, we know the slope minus 20 dB per decade. Okay, from 0.1 to 1, it's a 1 decade. Okay, so let me say this is 1 decade. Okay, and this is another decade. Okay, so in 1 decade, the magnitude is decreasing by 20 dB. Okay, so that's why at omega equal to 1, we have 0 dB, right? From 20 dB, now the magnitude has decreased to 0 dB. Again, if we go one more decade above, that is at other frequency omega 2, which is equal to 10, you will have again your magnitude will decrease by 20 dB, right? So from 0 to minus 20. Okay, so that's why omega 2 is 10. Okay, are you clear? It's
Yes,
not
sir.
required. Okay, okay, but the original question was to find out the poles and zeros. Okay, okay, we know we have two zeros. Okay, but let's also consider the initial slope. Okay, so initial slope is minus 40 dB per decade. Okay, so what does this convey? The poles at origin, right? We have seen. So now the slope is minus 40 dB per decade. So how many poles we have at the origin? Can you tell me number of poles at origin by seeing the initial slope? Okay, these are equal to 2 because minus 40 dB. Okay, so we have seen, like, if you have zero slope like this, okay, no pole at origin. If you have slope of minus 20 dB per decade, then one pole at origin. If you have two poles at origin, then minus 40. If you have three poles at origin, then you have minus 60 dB per decade. Okay, so just refer to the Bode plot topic. Okay, we have seen how to find out the poles at origin. Okay, so in this question, okay, two zeros and two poles. Okay, so this one is the correct answer, but we need to find out the transfer function. Okay, so what is the transfer function? We know k is square. Okay, so this is the transfer function we know. Okay, so can we find out the value of k? So you see the Bode plot, we have the Bode plot and we have the transfer function. So only missing term is k. I'm asking you, can we find out the value of k? Because see, magnitudes are given at different frequencies. Okay, so what you need to do, you need to find the magnitude, right? So okay, let me write this transfer function in this form. Okay, so it will be k into s plus 0.1 and s plus 10 by s square. Okay, this is the transfer function. Now if I find the sinusoidal transfer function and then find the magnitude, okay, which will be j omega plus 0.1 so the magnitude is equal to okay, okay, this we know. Okay, so this we know, and also what other information we have is at different frequencies, okay, like omega 1 and omega equal to 1 or omega equal to 2, we also know the magnitude, right? We can just equate that. Okay, let's suppose at omega equal to 1, we know the magnitude is equal to 0 dB. Can we not equate this? We can make this as 1, we know that, because if in dB it's 0 dB, then the magnitude is what? 1, right? So k 1 square plus 0.1 square 1 square plus 10 square by 1 square. Can you find out this value? Okay, so k is equal to 1 by 1 plus 0.1 square, okay, into 1 square. Let's do some approximation. So I'll just write 1 into 100. Okay, 100 is 10. So it is equal to 0.1, right? So now the transfer function is 0.1, okay, s plus 0.1 s plus 10 s square. Okay, so this is the transfer function, which is not asked in the question, but we are given with enough information, we can easily find out the transfer function. Okay, so I could have also used other omega values. Okay, at omega equal to 1, I know 0 dB, but you can also find out the same k value if you use omega equal to 10, then your magnitude is equal to minus 20. Okay, same thing. So any doubt in this question?
No, sir.
Okay, very simple question. We just extended this question. Okay, go to the next question. Okay, this is interesting. Consider a feedback control system shown below, which is subjected to unit step input. Our system is stable and has the following parameters. Okay, the steady state value of z. Okay, just see this transfer function. Okay, we know this is controller, right? Can you tell me what type of controller this is by looking at the coefficients ki, kp? You know, this is plant. Okay, so this is
Sir,
PI
for
controller. Yeah.
yes,
Okay, and we need to find out the value of z. Okay, so we need to find out the value of z. Okay, so what you know, this is y of s, you know, this is rs. Okay, and what we know, this is equal to e of s, right? Error. Okay, so what is zs? Zs is ki into s into e of s, right? Okay, we need to find the steady state value of z, that's fine. Okay, but z is what? Z is equal to ki into s into e of s, right? We need to find the steady state value. Okay, let's steady state. Okay, so we'll use the initial value theorem. Okay, which is this, and which is equal to z into what is z is ki into s into e of s. Okay, so do you have anyone has any doubt in this first? Z is equal to ki into ki by s into e of s, y I have written. Okay, just see this. Just see this. Okay, we need to find out z, right? And what is z? Z is equal to e of s into ki by s, right? That's what I have written. And I need to find the steady state value. It's asked in the question. And steady state value is limit s tends to 0 s into zs, right? Same thing we used to do with the error. And zs, now I know ki by s into e of s. Okay, basically what I need to find out is this error. Okay, if this is the thing I need to find out, just if I know what is the value of e of s, I will know what is the steady state value of z. Okay, now let's find out what is e of s. Okay, so directly I can write e of s as rs by 1 plus gshs. Anyone has any doubt in this? How this, how I have like came to this e of s equal to rs by 1 plus gshs? In our question, see, it's very simple. What is gs? Gs is cs into ps. Okay, but the generic form is this. Any doubt? Okay, can you okay, can you just switch off your microphone?
ಚಪಾತಿ ಮಾಡೆ
Hello?
ಚಪಾತಿ ಮಾಡೋದಾದ್ರೆ ಆಗಂಗ್ ಮಾಡ್ಬೇಕು ನೋಡಲ್ರಿ ಹತ್ತು
Excuse me?
ಅಲ್ಲಿ 4 ಜನ ಅಂದ್ರೆ ಒಂದು ಮಿನಿಮಮ್ ಅಂದ್ರೆ ಒಂದು 10 12 ಇರ್ಬೇಕು.
Okay, so directly I'm writing this, right? It's very easy. You can just go back to your lectures and derive also. Okay, just find the relations. Okay, so E of S is equal to RS divided by 1 plus GS into HS. Okay, so let's find out GS. GS is CS into PS. Okay, and CS is what? Controller transfer function. So what is controller transfer function here? Very simple. So CS is PI, right? So KP plus KI by S. Okay, so this is CS. KP plus KI by S. What is PS? PS is already given, that is second order transfer function. Okay, so let's use the values. Okay, let me write the PS here. Omega is 500 square. Okay, square plus 2 zeta. Zeta is 0.7 into omega n, which is 500 plus omega square. Okay, there is a S term also here. Plus 500 square. Okay, let me use this value. Okay, and what is Kp and Ki? Kp value is given as 4 and Ki is 10. Okay, so this is 4 plus 10s, okay, into 500 square, or okay, so this is given. Okay, so let's find E of S. E of S is, R of S is given, it's a step function. Okay, so R of S is equal to 1 by S. Okay, so 1 by S, 1 plus GS into HS. HS is equal to 1, which is 10 by S. Okay, the same thing. Okay, let me use this E of S in the original equation. So ZSS is equal to limit S tends to 0. Okay, so Ki was also there. Ki into E of S. Okay, Ki into E of S. So what is E of S? The same, this value. Okay. And Ki is equal to 10. Okay, so let me just simplify and we'll just put the limits. Okay, so this is 10 by S into, in the numerator you will get S square plus 2 into 0.7 into 500 S plus 500 square. Okay, and in the numerator what you'll get this 500 square. Okay, and also you'll get one more S. Okay, here you'll get S. Okay, this is, so that I'm writing here. Okay, so this will be multiplied by S plus 4S plus 10 into 500 square. Okay, so let's So if you put S, what you'll get, you put the S 10 into, you get 500 square from the numerator, okay? And from the denominator, if you put S, you'll get 10 into, again, 500 square, okay? So you'll be remaining with this, okay? Because, you know, S gets multiplied. That means if you put S equal to 0, this terms gets 0, okay? And this, again, these terms are getting 0. And this is also getting 0. That's why I'll be left with the numerator and denominator having same values, okay? So which will be equal to 1, okay? If you apply the limit, you'll get, sorry, this is not E of S, this is Z steady state value, which is equal to 1. Okay, so the answer is 1. Okay, so any doubt in this question? Very simple. Steady state value of Z we need to find out. Okay, first find out what is ZS. ZS is Ki by S into E of S, right? Steady state value is, if you want to, you'll apply the initial value theorem, right? Where limit S tends to 0, S into ZS. Okay, so from here I'm getting ZSS is equal to Ki into E of S. Okay, so E of S I need to find out. It's very like generic. You should remember E of S is R of S by 1 plus GS into HS. Okay, and what we need to find out, everything is given. RS is given, GS is CS into PS. Okay, so just plug in into ZSS and you'll get to this. Okay, ZSS equal to 1. Any doubt in this question? So this is gate question. Okay, simple question, but just mistakes can happen, right? Okay, we'll go to the next question. Let me see how many questions are left. Okay, we'll do, this is a root locus question. Okay, we'll do the root locus question. So the characteristic equation of the closed loop transfer function is given. Okay, is k is greater than 0. Which one of the following statement is true? Okay, so if you see, so from the option you can see it's a root locus. Okay, question, its roots, it cannot have a breakaway point and this thing. Okay, so we have to build the root locus and find out the, or answer this question. Okay, so closed loop system characteristic equation is given. Okay, so you know, you can write the transfer function, or you can know the open loop transfer function by writing this in this form. Okay, is equal to 0, and you know g of s, this is open loop transfer function to be this. Okay, where k is greater than 0. Okay, so this is GSHS. Okay, because it's not given in the question, it's a unity feedback or not. Okay, because you know this is 1 plus GSHS equal to 0, and we are finding out GS and HSS, which is open loop transfer function. Okay, so let's build the root locus. Okay, this is S plane, right? real and imaginary part. Okay. So first we'll plot the first step was to plot the open loop zeros and poles, right? So what can you say about the zeros? Has only one zero, right? Minus 2. M is equal to 1. Okay. And what about the poles? We have at 0, minus 1 and minus 3. Okay. So n is equal to 3, right? So let's plot it. So we have at pole at 0 by cross, this is minus 1, and we have a 0 at 2, minus 2, and again we have a pole at minus 3. Okay, so we have plotted the open loop zeros and poles. So next step was to find out the root locus on the negative axis, no, negative real axis. Okay, so let's find out like what we used to do. We used to choose some locations and we'll see on the right hand side whether there are odd number of open loop poles and zeros. Okay, so let's check one by one. Okay, so if I take a test point here, so and see on the right hand side, okay, how many poles and zeros are lying? 1 2 3 4. Okay, so what can I say? If it's even, what we say? Can you tell me? Root locus will exist on? Huh?
Sir, the test point will not lie on the root locus.
Correct, because we have even number of poles and zeros, right? That's why. Okay, so we don't have the root locus from minus infinity to minus 3. Okay, and if I take the test point here, okay, if I take the test point and if I see on the right side, I can see 3 number of poles and zeros. Okay, so the number is even, so what I can say, the root locus will exist, right? So root locus exists from here. Okay, I'm just referring, or I'll just mention by highlighting these points. Okay, so root locus will exist from minus 3 to minus 2, and again if I choose a test point here, so what I can see is on the right hand side of this test point, 2 open loop poles and zeros, number is even, right? So no root locus exists in this range minus 2 to minus 1. Okay, so again if I take a test point here, so what I can see on the right hand side, only one pole exists, the number is odd. Okay, that means root locus will exist. Okay, so we have found out 2 regions where the root locus will exist. Okay, so again let's see the options. Okay, its roots are always real. Okay, okay, so the first point, option A is clearly false. Okay, so you can see directly, since we have already seen the root locus, so you already know. Okay, a breakaway point will exist here, right, between minus 1 and 0, and root locus will go like this. Okay, and I'm just drawing rough because already we have seen so many examples. Root locus will like this, the root locus will exist. Okay, because there are 2 poles, and at one point here at k equal to some point they will break away, right?
Sir, sir,
Yes.
sir, can you explain how to operate online calculator, sir, in NPTEL?
NPTEL. So I have not used that. So it's a gate calculator or like some other calculator?
I don't know, sir. In NPTEL, which calculator? If it is gate calculator, I am able to know, sir. But if it is on a Google calculator, how to operate it, sir?
If they are, I also don't know. Like I've not seen like which calculator to use. Like in Gate, it's okay. You'll have apps where you can find out. But you better get familiar with the Gate calculator, okay? Because functionality is almost of all the online exam, like it's similar to that.
Okay, sir.
Okay. Because I also don't know like what type of calculator they provide in the exams. Okay. So returning to the question, so I know basically this is how the root locus is going to look like. Okay. So I can answer this question. Okay. Its roots are always real. Okay. So what about the option A? So since the root locus is breaking out, okay. So at these points, any point here, root locus is not real. Sorry, the value is not real. Okay. So the first statement is wrong, right? Because we can have a complex values also for this transfer function as k is varied. Second option is it cannot have a breakaway point in the range of -1 to 0. So, but no, we have seen root locus exist, and since two poles are there at -1 and 0, there will be one breakaway point. Okay. So up to second of step 2 is fine. The third step was to find out the number of root locus that are going to infinity, right? So how to find out? Okay, by using this n minus n. So n is equal to 3, m is equal to 1, 2. So two root loci will go to infinity, and these are two root loci that I have drawn here. Okay, that also we can confirm. So second statement is also wrong. It cannot have a break. It has a one breakaway point. Okay, and how to find out the breakaway point? Because I'm not doing this. Breakaway point is, you have this 1 plus k into s plus 2, okay, s into s plus 1 into s plus 3. Okay, you used to assume this some function PCL, right? And what you do, you differentiate with respect to s, okay, and you find out what is the value of s where it becomes 0, okay, and you find out the value of s, okay, and that for that particular value of s, what is the value of k, and the k should be greater than 0 because it's given in the question k is greater than 0, okay, and that is that value, okay. So whatever the value of calculated is this value, okay. This is how you find out the breakaway point. Okay, I think if you solve this question, a breakaway point will be minus 0.5 something. Okay, I'm not calculating, but when I'll do the solution and provide this. Okay, but I'm not discussing that. Okay, this is how you'll calculate the breakaway point. And third option is two of its roots tend to infinity along the asymptotes, right? So this was number of root loci going to infinity. Okay, so which was n minus m, which is 2, right? So two of its roots tend to infinity. So this option is correct. Okay, the last option is it may have a complex root in the right half plane. So you can see, okay, so a root locus is not going into right half plane. Okay, so that's why this option is also wrong because it's going to infinity. Okay, because you can find the asymptote also. How to find the asymptotes? Angle is plus minus 2q plus 1 into 180 degree n minus m, right? And if you substitute the value of q and m minus 1, let's do that. Because n minus 1 is equal to 2, we anyway know that, and we need to find two angles, right? So one will be plus 90 degree, other will be minus 90 degree. Okay, so here also you can see this is plus 90 and minus 90 along the assumed roads. Okay, first you have to find the center, that not a problem. Okay, but this statement is also false. So any doubt in this question? I'll solve this and upload this, no problem. But at least you know, like how to draw the root locus. Okay, and how to answer this. Very simple question. This is again very simple question. Okay, and I'll go to the next question. So it says if the loop gain k of negative feedback system having a loop transfer function of this is to be adjusted to induce a sustained oscillation, then okay, let's find out. G of s is given as k into s plus 3 into s plus a. So you know, for sustained oscillations, your real part should be equal to 0 and the root should always lie in the on the imaginary axis. Okay, frequency of oscillation, sustained oscillation, right? Sustained oscillation means your poles are lying on the imaginary axis, or the closed loop poles are on the imaginary axis. So one way is you can find out from the root locus, and other way is we used to do the Raoult's stability criteria. Also there also you can find out. So let's use that Raoult's stability criteria. Okay. So what is that? First find the characteristic equation. The negative feedback. Okay. Okay. So characteristic equation is this. So what is this? S square plus 16s plus 64 plus k into s plus 3k. Okay, which can be written as 16 plus k s plus 64 plus 3k. Okay, apply criteria. Okay, so you can say it's a quadratic equation, right? So all the coefficients should be positive, because if you see the coefficient of s square, which is equal to 1, right, which is positive, so 16 plus k should be greater than 0 and 64 plus 3k should be greater than 0. Okay, so that means k should be greater than minus 16. Okay, from here if you find out the value of k, what you will get, k should be greater than 64 by 3. That is, yes, this is negative, right? Minus k should be greater than minus 64 by 3. So what is this value? Can you tell me this value? 64 by 3.
So 21.33.
21. Let's take, okay, 21.33. Okay, so that means we have to take this value. Okay, k is greater than minus 60. We ensure this, we are fine. Okay, so but we have to find the frequency, right? So what we used to do, let's build the Raoult's array. So coefficient is 1, 16 plus k, and other coefficient is 64 plus 3k. Okay, so if you fill this, you'll get here 64 plus 3k. Okay, and how we used to find out, okay, if this is equal to 0, right? If at k equal to minus 16, okay, so this row is equal to 0, then what we used to do, we used to take the auxiliary equation by using this row, right? So this is s square plus 64 plus 3k, okay, equal to 0, okay, and used to put value of k here. So s square plus 64 plus 3 into minus 16 equal to 0. So what is this? Square plus 64 plus 3, 16 into 3 is I think 48. So this is again 16. Okay, so s is coming. Okay, so I'm getting this 4. Okay, so as to so I'm getting sustained oscillation at omega equal to 4. Okay, but in this question, okay, let's see the options. Okay, clearly you can see the frequency of oscillation must be 4. Okay, this option is there. Okay, but one option also we have, because here it's not given though, but k is negative, right? You can see here. Okay, k is coming out to be negative. This is one problem here. Okay, though it's not given, let's also try to find out the root locus for this. Okay, so this is the transfer function. Let's find out the root locus. Okay, so okay, so we have, let's first plot the poles and zeros. Okay, so only s equal to minus 3, we have 1 0, and 2 poles at minus 8. Okay, so I hope I'm writing it correctly. K into s plus 3, s plus 8. Okay, okay, so let's assume that k is positive. Okay, k is positive, and for positive values, let's find out the root locus. Okay, so on the real axis, I can see root locus will exist here. First, you know, root locus will exist here. Okay, because you know, 2 poles and 1 0 on the right hand side, and root locus will also exist here because only one pole, right? Sorry, 0. And after minus 3, root locus is not there, right? So I've taken 3 test points here. So if I take the test point here, I can see 3 number of poles and zeros, right? 2 pole and 1 0 is total 3. Here if I take only 1 0, 1 is even. So here also exists. Or if I take here and see to the right, I don't have any poles and zeros. That's why the root locus does not exist. Okay. So the highlighted portion is where the root locus exists. Okay. And what is m here is equal to 1 and n is equal to 8, sorry 2, right? And what is n minus m is equal to 1, which is also equal to number of root locus going to infinity. Okay, so what I can see is one root locus is going like this and one root locus is going like this. Okay, so this is for k. For k greater than 0, okay, for k greater than 0, this option is true. Such a k does not exist which induces sustained oscillation, right? For k greater than 0. Okay, you can see it's not going to imaginary axis, right? It's always lying on the real axis. That means sustained oscillation is not there, imaginary part is not there. Okay, so let's also build the root locus for k greater than, sorry, k can be negative in this case. Okay, so rules are opposite, right? So what I can see is okay, minus 8 and minus 3. Okay, so rules are opposite, and that means I'll have root locus here, here. Okay, I'll only have a root locus here. Okay, so what will happen? So breakaway point you have to find out. Okay, so it will get lengthy. Okay, so let me draw the rough diagram of how it should be. What I am assuming is it's going somewhere. Okay, like this. For that I have to find the assumed rates and all, and one will be going to 0 and again will be going to infinity. So here, okay, these points we have calculated. K equal to 16. Okay, so at this point we have, what is the value of S plus minus j omega? So this what we have calculated. This is plus j omega and this is minus j omega. Okay, you just verify whether this is something else or this thing. What I know is it should cut the imaginary axis at a point, and that point already we have calculated from. Okay, but this is for k equal to negative values. Okay, and what can we say for k greater than minus 16? Okay, k greater than minus 16, because k is varying from minus infinity to 0, right? So what we can say, this portion is which portion? Where the roots are always positive. Though k is negative, right? Here k is negative, but k is greater than minus 16. Okay, because this is 0 point, right? This is k equal to 0, right? And this point is k equal to minus 16. Okay, I hope I made it clear. Okay, from root locus also see, but in the question it's not given, right? These two options are true. This is also true, and this is also true for k less k is negative. Okay. So any doubt in this question? Okay, we can verify from the root locus also. Yes. Okay, time is there. Okay, let me just do one more question. Okay, because other questions are very simple. Okay. Okay, this is the I think, last question. Okay, this question I will do Nyquist plot code. Okay, because other are very easy. So the open loop transfer function of unity gain negative feedback system is given as this. Okay, so Nyquist contour in the S-plane encloses the entire right half plane. Okay, and a small neighborhood around the origin in the left half plane. Okay, in this it's slightly different as to what we have studied. It's also taking the origin also, right? You can see the contour. Okay, the number of encirclements of the point -1 plus 0 by the Nyquist plot corresponding to Nyquist contour is denoted as S. Okay, then we have to find out the value of n. Okay, fine. We know n is equal to z minus p. Okay, where we know n is number of encirclement. Okay, so this is around -1 point in clockwise direction, right? Clockwise direction. Okay. And what is z? These are the closed loop poles in right half plane. Okay, and p is of closed loop transfer function, right? And what is p? This is open loop. Let me write it. Open loop poles in RHP. Okay, so we have to find out the encirclement n. Okay, and we are given with GS. Fine. Okay, this is the transfer function. Okay, so what can you say about P? Open loop poles in RHP. So that was our definition. Okay, but here you see the contour, right? Now the contour is this. This is the contour, right? And I'll just replace this. Okay, that was the basic definition, right? We used to take the right half plane, but in this case we are taking the Nyquist contour that is also going to the left. Okay, and we have a, if you see S into S plus 1. Okay, so in this case we have a pole here at origin, right? So in this case P value is equal to 1, right? Because of the Nyquist contour that we have chosen. You can see number of poles, open loop poles lying in this contour. And how many poles are lying in this contour? 1. That is at origin, right? That's why P, the value of P is equal to 1. Okay. Now we have to find out Z minus P. Sorry, P is already known, that is equal to 1. If I know the value of Z, I can find out the value of Z, N. Okay. So N is the number of closed loop poles in RHP. Okay. So simple thing is I can find the closed loop pole. How to find out the closed loop pole? I can do this one plus GSS HS equal to 0. Okay, so if I do this, I can easily find out the closed loop poles. Okay, and what are the closed loop poles here? Minus b, sorry, this is s plus minus b square, which is 1 minus 4 into 1 into 1, 2 into 1. Okay, so this will be this value, j into root 3 by 2. So what you can see here, let me write it like this, j into root 3 by 2. Okay, so I can see both the roots are lying on the in the left half plane, right? Because what I can see is real part is always positive, right? In this plane, what is there? The roots are lying somewhere here. Minus 1 by 2 plus root 3 by 2 and here. Okay, so this is what left half plane. Okay, so from here I can say the value of z is equal to 0. So no closed loop pole is lying on the right half plane of S plane. Okay, that from the 1 plus GS I have found out. So I know I need to find out the value of n, which is z minus b and 0 minus 1. N is equal to minus 1. Okay, so I'm getting what? N equal to, I'm getting minus 1 is not there. Okay, did I miss something? Okay, I'm getting n equal to minus 1. That is encirclement in the anti-clockwise direction. Okay, so another method is to build the Nyquist plot. Okay, so what you do, so this I'm not doing now. Okay, so when I upload the question, I will also build the Nyquist plot. Okay, then you can verify it. Okay, so because in Nyquist plot you have to vary zero the frequencies from minus infinity to infinity. Okay, so I will do that and I will upload the complete solution. Okay, for other part also. So I partially whatever this question like what they have asked. So I have not done the question, but it's a very simple question. Okay, simple properties that we have studied here also. Very simple question. So I'll do the solution and I will upload the final this notes for today. Okay, so any doubt for today's session? I'll close the session because time is up. So simple questions. Okay, so I've done the gate questions, very simple. So a part was asked, but I try to do the whole. Okay, where I can. These are very simple questions. So if you are writing exams, okay, so I don't know the format like objective or subjective question, but if the format is objective questions, then you can practice gate questions. Okay, very simple gate questions. But in case it's a subjective question, then try to find out the like Bode plot from starting to like how to plot the Bode plot, right? Root locus, what other the number of steps we do, and how to plot the Nyquist plot. Okay, this type of question. So you can easily do it, simple, but you have to practice this. Okay, so any doubt for today's session? Okay, so you can do a question with number of ways like I have done today. Okay, okay. Link for the calculator is also given. Okay. Okay, any doubt? So all the best for the questions. and because for the exams. Okay. So this is our last session. So I'll just tell you who I am. So I'm basically a PhD scholar. So I'm in my third year doing my PhD in power electronics. Okay, basically on gate driver side. Okay, so but this course was introduced from engineering design department. So that's a separate department. Okay. So you can reach me if you have any doubt. Okay, so I'll give you my email address. Okay, so this is ee21d024 so all in small letters .iitm.ac.in. Okay, so in case you have any doubt regarding control system questions, okay, you can mail me. Okay, I'll try to follow up. Okay. Okay, if you have any doubt, I can answer them. Otherwise, I will close the session. Okay. I will upload this notes with complete solution, no problem. Okay. Okay then. So thanks for attending lectures, not this lecture, like all the lectures, like some of you are like regulars. So thank you very much. Okay, all the best for your exam, NPTEL exam. Thank you.